In 7.3, we are solving exponential equations. An exponential equation is one in which the variable occurs in the exponent. So our first challenge is to understand how to remove the variable from the exponent. Because when it is stuck up in the exponent spot, we cannot solve for x. And that's what we want to do. We want an answer that is x equals. We need to get the variable from the exponent. All right, so how do we do that? To solve exponential equations, we are going to need to apply the exponent laws. You learned exponent laws in previous math classes. You are going to, we don't have time to review them all here, but we will look at the few that we need to use. One method of solving exponential equations is also using the following property. So we will be using our exponent laws, and then the most important part of helping us remove the variable from the exponent is going to be this property. If a to the power of x equals a to the power of y, then x equals y. That is super important. Basically, if we have two powers that are equal and their bases are equal, that means their exponents are equal. And look what happens when we do that. When we go from having powers and then we equate the exponents, we are taking those variables out of the exponent, which is what we want to do. So we are going to use our exponent laws. We are going to use this property to equate the exponents, and then we're going to solve. Here are the specific steps to solving exponential equations algebraically. Step 1 says, determine if the powers can be written using the same base. So this very first step, this step right here, determine if the powers. I don't really have a step-by-step process for you to be able to determine if the powers can be written using the same base. What you are going to be using here to decide is some number sense. You need to be able to look at a given base and decide if it can be written as a different base. So it's just based on your experience with numbers and your ability to recognize when we can change a number into a different base. If we can write the powers in the same base, we will do so. So that might require us to do a little bit of work in terms of some numbers. In step 2, here we are going to use the properties of exponents. Those are our exponent laws to simplify the equation so that you have one power equal to another power. What I always say that we are looking for is we are looking for a single power of the same base on both sides of the equation. We want a single power of the same base on both sides of the equation. And in addition to that, we want to make sure that our exponents are also as simplified as possible. In order to do that, in order to obtain a single power of the same base on both sides of the equation with simplified exponents, we are going to have to use our exponent laws. Again, we are not going to review them here, but I will alert you to them as we use them. Once we have a single power with the same base on both sides of the equation, in other words, once we have a to the power of x equals a to the power of y, our third step is to set the exponents equal to each other. So here is where we are using that property that we talked about up here. Single power, same base, equate the exponents. When we do that, what we're going to end up having is either a linear or a quadratic equation. And so our fourth step is to solve that equation. So our fourth step might actually be a few steps, but that we are solving either a linear or a quadratic equation. Usually linear, but it could be quadratic. So just keep in mind that we may have to do that. Now, those are our steps for solving algebraically. Exponential equations can also be solved graphically. So just like we did in previous chapters, radical, rational, and polynomial equations, the exact same steps we can use to solve exponential equations. What we mean by that is we can find the intersection point of a system of two equations. In other words, we take one side of the equation and put it into y1. We take the other side and put it into y2, and then we find the intersection point, or points if there is more than one. On the other hand, we could take our equation and set it equal to 0, so move everything to one side of the equation, or maybe the equation is already set up where it's equal to 0. In this case, we would put the whole function into y1, and we would find the x-intercept, or x-intercepts. Please keep in mind that when we solve by graphing, no matter what kind of equation we are solving, we are going to state the x value only of our point that is where our solution is. So we're going to state the x value only. So point of intersection, x value. X-intercept, x value. Let's go ahead and solve some. So in this example, we are going to algebraically solve those exponential equations. We're going to check our solutions, and we are going to check it graphically. So we get that practice of solving graphically as well using our calculators. All right, here's our first equation. 3 to the power of 2x minus 7 equals 3 to the power of x plus 2. Step 1, get both sides into the same base. Already done. Base of 3, base of 3. So step 1 is done. Step 2 is to use our exponent laws to simplify. So we have a single power on both sides with simplified equations or exponents. Already done. Base of 3, exponent, base of 3, exponent. That step 2 is done. Step 3 then, equate the exponents. So we have 2x minus 7 equals x plus 2, and there is a linear equation for us to solve. Start by subtracting x from both sides. 2x minus x is x minus 7. The x is gone from the right-hand side. We're just left with 2. Add 7 to both sides, and x is equal to 9. So step 1 and step 2 were already done for us. All we had to do was use that property to equate the exponents and then solve the linear equation. Let's go to our calculator now to graph and see if we get that same solution. So into y1, we're going to put the first exponential equation, which was 3 to the power of 2x minus 7. And into y2, we're going to put the other side of the equation, 3 to the power of x plus 2. I'm going to hit zoom 6, just go to that standard window setting to start. There's going to be one exponential function. Here's the second exponential function. Now I can't see the intersection point, but I'm going to see if the calculator can find it anyways. If not, we may have to adjust the window. So enter for y1, enter for y2, and enter for guess. And we're looking for the x value, and there it is. The x value is 9 for our intersection point, and our solution was 9 when we did it algebraically. Let's look at B. 11 to the power of 2x plus 6 equals 121. So we, first of all, can see right away, not in the same base. Our base here is 11. Our base here is 121. So we need to write these into the same base. And because I recognize 121 as 11 squared, I know that I can write both sides into the same base. So we're going to do that. We're going to leave that the left-hand side alone, but the right-hand side, we're going to rewrite as 11 squared. So we haven't changed anything. 121 and 11 squared are equal. We haven't changed anything about the equation, just what it looks like so that both sides are in the same base. Single power on the left side, single power on the right-hand side. So we can go to step 3, use the property to equate the exponents. 2x plus 6 equals 2. And we have an even easier linear function. Subtract 6 from both sides. 2x is equal to -4. Divide both sides by 2. And x is equal to -2. So a little tougher than part A, because part A, most of the work was done for us, but not too bad. We just had to write that right side with the base of 11, equate the exponents, and then solve. Let's go to the calculator and check our solution. So into y equals, let's clear out what we had from there before. Let's put the left-hand side into y1. So 11 to the power of 2x plus 6. And then into y2, 121. So when we're checking, I'm going back to that original equation that was given to me. I don't go to where I changed anything. Now again, I'm going to have a hard time seeing that intersection point because this is a constant at 121. But let's see if the calculator can find it anyways. Second trace number 5 for intersect. Enter 3 times. And it can find it. And again, we're going to look at that x value only, x equals -2, which matches our algebraic solution of x equals -2. All right, part C, bit more of a challenge with part C. 9 to the power of 2x minus 3, 27 to the power of x plus 4. So I can see right now different bases, and I also recognize that I cannot write 9 with a base of 27, and I cannot write 27 with a base of 9. So what we're going to have to do in part C is we are going to have to change the base on both sides. So a bit more of a challenge here. In part A, we didn't have to change the base at all. It was already in a base of 3. In part B, we only had to change the base on the right-hand side. Here, we're going to have to change the base on both sides. Now, what base is going to work here? We are going to use a base of 3. Now, how do I know that? I know that because I know my powers of 3. So if you start, or when I started talking about number sense up here, what I'm talking about is you should know at least the first 3 powers of bases from 2 to 9. So you should be able to know them and recognize them, and it's going to make these steps here of deciding what base to use a lot easier. So we are going to change them both to a base of 3. 9 can be written as 3 squared. So I'm going to take the 9 out and replace it with 3 squared. Now that exponent that was to the 9 is still there. So it's just the 9 that's becoming 3 squared. The exponent stays. And same thing with the right-hand side. 27 is 3 to the power of 3. So I've replaced the 27 with a base of 3, but that exponent of x plus 4 is still there as well. So it makes it look way messier, but at the very least, we have a base of 3. So step 1 is done. Both sides are in the same base. Step 2, we need to simplify so that we can get it to that single power on both sides with simplified exponents. We are going to use an exponent law here. We're going to use the power to a power law. And when we have, let's say we have a base x, and we raise that to an exponent a, and then we take that power and raise it to another exponent b, we can simplify that by keeping the base and multiplying the exponents, a times b. So here, when I have 3 to the power of 2 to the power of 2x minus 3, I'm going to multiply these exponents. Because I have a coefficient and a binomial, when I multiply, we have to distribute. So our left-hand side is going to become 3 to the power of 4x minus 6. So I'm using that exponent law to simplify that right-hand side We need that single power with a simplified exponent. Same thing on the right-hand side. We have a power to a power. We need to multiply these exponents. We have a coefficient to a binomial, so we need to distribute. This becomes 3 to the power of 3x plus 12. Now, although the equation that we have here looks very different than the equation we have up here, it is completely equivalent. We took the 9 and replaced it with 3 squared. We took the 27 and replaced it with 3 cubed. The value of those bases are still the same. We just changed the base we were using. All right, we have a single power on both sides, same base, simplified exponents. Step 3, equate the exponents. So 4x minus 6 equals 3x plus 12. Again, I'm going to need to get my variables together. So I'm going to subtract 3x from both sides. I'm also just going to move over here. 4x minus 3x is just x. So we're left with x minus 6 on the left-hand side, 12 on the right-hand side. Add the 6 to both sides, and we are going to get x equals 18. Sorry, so we add the 6 to both sides, and we get x equals 18. And that would be our solution. So a bit more work with part C. Again, part A, not very much work at all, went straight to equating the exponents. Part B, we had to change the right-hand side to a base of 11, equate the exponents. Part C, change both sides to a base of 3, use the power law to simplify, equate the exponents. Let's go to our calculator and let's check our answer for part C. Again, we're going to go back to the original exponential function. So don't use any of the simplified forms when we check. We're checking the original equation that was given to us. So 9 to the power of 2x minus 3 into y1, and then into y2, 27 to the power of x plus 4. Now, when I graph this, we probably won't see the intersection point, and I will have to change my window settings here. I already know the answer should be 18, but because my window only goes to an x maximum of 10, we're not going to be able to see it. So I'm going to go to an x maximum of 20, sort of cheating a little bit. I already know the answer, so I know what I'm looking for. Second trace, number 5 for intersect. So there's our two exponential functions. Okay, it's having a hard time finding it. There we go. Oh, first curve, y1, yeah, enter. Second curve, enter, guess. We're looking for that x value. We're hoping it pops up as 18. Let it think for a second. And there it is, x equals 18. Perfect. Part D. Now, part D looks a little weird because it looks like we don't have an exponent on this side, but we do. So I'm just going to remind you of an exponent law that we have when we have a rational exponent. So when I have x to the power of m over n, when we have an exponent that's a fraction, that actually implies that we have a radical. So we can write this as, we write the radical sign. The denominator of the exponent becomes our index. Our base is our radicand. And the numerator of our exponent becomes our power. So we have to remember that a rational or fraction exponent means we have a radical. So in this question here, we do have a base of 7 and we do have an exponent there. That exponent is going to be 1 over 2. So our index is 2, even though we don't write it. And our exponent there is 1. So we're going to rewrite this side as 7 to the power of 1/2. Also on the other side, we can see that we have a 49 there. Right now, 7 and 49 are not in the same base, but using my number sense, I know that I can take 49 and I can write it as 7 squared. So I'm going to take the 49 out, replace it with 7 squared, but I still have to leave that exponent of x minus 3 there as well. So take that left-hand side, recognize that a radical can be written as a fraction exponent. In this case, that fraction is 1/2. Right-hand side, recognize that 49 can be written as a base of 7, and now both sides are in the same base. Let's simplify a little bit. The left-hand side can't really be simplified at all. I'm just going to leave it as 7 to the power of 1/2. On the right-hand side, again, power to a power. We need to multiply those exponents. Again, coefficient times a binomial, so we're going to distribute 7 to the 2x minus 6. We have a single power on this side, single power on the other side, same base, equate the exponents. So 1/2 is equal to 2x minus 6, and then we are going to solve the linear equation. We're going to start by adding 6 to both sides. So 6 is like 12 over 2. 12 over 2 plus 1 over 2 is 13 over 2 is equal to 2x. Divide both sides by 2, and x is equal to 13 over 4. Oops, just x over there. You're welcome to do this in decimals as well. I left it in fraction form, but you could also do this just as easily. Call the 13 over 2 6.5, divide both sides by 2, and we get 3.25. So you could do this as a decimal as well. Let's go ahead and check that on the calculator. Go to y equals. Let's clear out what we have in there. One side is the root 7. Other side, 49 to the power of x minus 3. Oops, bracket there first. And then let's find the intersection point. I'm going to go back to the standard window because I know I adjusted it a little bit. There's our constant. That's the 7 to the 1/2. It's a constant. There's our 49 to the x over x minus 3. We can actually see the intersection point this time. Enter, enter, enter. Should be at 3.25. Look at that x coordinate. You bet it works. So in this one, we are really only changing the base of one side, but we're also recognizing this exponent law, that when we have a radical, it means we have a rational exponent. Let's have a look at E, and E is going to test us in a couple of different ways. So we have 1 over 64 to the power of x minus 2 equals 4 times 16 to the power of x plus 3. First things first. I know that what you want to do is you would like to try to multiply these two guys together because they're so close to each other, but please do not do that. You cannot multiply the 4 by the 16. Our order of operations, brackets, exponents, then division and multiplication. So this 16 is committed to its exponent. It cannot go multiplying with the 4. By order of operations, it has to go to its exponent first before it can get multiplied. So even though they're so close together and it would be so nice if we could put them together, we cannot. We have to follow the order of operations. So be really, really careful with that. So that's the first thing. Please make sure that you don't try to just put numbers together because they look nice. Make sure that if one of them is a base, we can't multiply them together. All right, none of these are in the same base. On the left-hand side, we have a base of 1 over 64. We've got two terms on the right-hand side. One of them is just a 4, and the other one is 16. I recognize that these three numbers, 1 over 64, 4, and 16, can all be written with a base of 4. So we're going to change them all to a base of 4. Okay, and that again is just our number sense. We need to be able to recognize those numbers. Okay, so we're going to take 1 over 64 and we're going to change it to a base of 4, which looks a little weird. But whenever I see a 1 over like this, what it tells me is that somewhere we must have taken the reciprocal of the base. And if we took the reciprocal of the base, that tells me that the exponent is negative. So really watch for when your base has a 1 over. What it means is that when you convert it to its new base, you're going to have a negative exponent. So 1 over 64 is equal to 4 to the negative 3. I know it's negative because it's a 1 over 64. It's been reciprocated. And I know it's 3 because 4 to the power of 3 is 64. So I've replaced the base, keeping that exponent still there. The x minus 2 is still there. On the other side, 4 is already in a base of 4. We can write it as 4 to the power of 1 if you want. You don't have to do that, but it kind of helps for the next step. Times 16 is 4 to the power of 2. So replacing that 16 with 4 squared to the power of x plus 3. So don't forget that when you change the base, that if there's an exponent already there, it stays there. Step 1 is done. Everything is written with a base 4. Step 2 is going to be to use our exponent laws to simplify. On the left-hand side, we have a power to a power. I need to multiply the exponents. I have a coefficient and a binomial, so we need to distribute. Our left-hand side becomes 4 to the negative 3x plus 2. On the other side, I'm just going to leave my 4 to the power of 1 for now. Here, also, power to a power. I need to multiply the exponents. I'm going to distribute that 2. So this is going to be 4 to the 2x plus 6. Everything is in the same base. I have a problem though. I don't have a single power on both sides. I do on the left-hand side. So left-hand side is good. We have a single power there. We've simplified our exponents. We don't have a single power over here. Notice that we have 2 terms here. I want to put these 2 terms together. So we are going to use another exponent law. So let me remind you about this exponent law. If we have a base x to a power a, and we multiply it to another power with the same base and a different exponent, we can actually put these 2 terms together. We can keep the base and we can add the exponents. So this rule only works if the bases are the same, and if we are multiplying, we can simplify it to a single term by adding the exponents. This is the situation we have over here. I have 2 powers. They both have the same base. They both have a base of 4. So I'm going to keep that base of 4, and I'm going to add the exponents together. So it's 1 plus 2x plus 6, which when we simplify becomes 2x plus 7. So we use the power to a power law for these 2 here, and then recognizing that we don't have a single power on this side, we use this exponent law, and this exponent law would be our product law. Now I have a single power on both sides, same base. We can now equate the exponents. 3x plus 2 equals 2x plus 7. And we can go ahead and bring our variables together. So subtract 2x from both sides. Negative 5x plus 2 is equal to 7. I am going to subtract 2 from both sides. So negative 5x is equal to 5. And then we are going, I saw a mistake here. This is going to be 6. 2 times negative 3 times negative 2 is 6. Sorry. So we're going to subtract 6 from both sides. And then we get a 1 over here. And then we would divide both sides by 5. And x is equal to negative 1 over 5. So sorry, I didn't distribute that correctly. Negative 3 times negative 2 would be positive 6. Okay, you could also write this as negative 0.2. You can write it as a decimal as well. There is our solution. Let's check that on our graph. So go to y equals. One more time, clear all that stuff out. Go ahead and put in left-hand side 1 over 64 to the power of x minus 2. And then 4 times 16 to the power of x plus 3. Again, I'm going to go to that standard window, so zoom 6. This one's going to look like exponential decay because of our base. And then the next one, we should see some exponential growth. I can't see the intersection point, but my x value is small enough that I should still be able to find it. We're looking for an x value of negative 0.2, and there it is. So this one is a little more intense. First of all, recognizing we can't put the 4 and the 16 together, recognizing that 1 over 64 is 4 to a negative exponent, which would be 3, using our power to a power to simplify the exponents here, using our product law to get a single power on that side, then equating the exponents. Let's have a look at F. So in F, I can see right away, not everything is in the same base. Also, I recognize that there's not much I can do on that left-hand side. I can't divide 25 by 125. The reason I can't divide is because each of them have their own exponents. So they're committed to their own exponents first before they can divide by each other. But we're going to do the same thing. We're going to start at the same place we started with all of these, and that's getting everything into the same base. I have a base of 25, I have a base of 125, and I have a base of 5. And so I recognize that all of these numbers can be written as a base of 5. So 25 is going to come out, and it's going to get replaced with 5 to the power of 2. We need to leave that exponent of x plus 2 with it. 125 is going to come out. It's going to get replaced with 5 to the power of 3. And that power of x minus 1 is going to stay there. On that right-hand side, 5 to the power of 3x minus 7, just going to stay, already a base of 5. Okay, so everything has the same base. We don't have a single power over here, but before I can do anything about it getting a single power, I am going to simplify the exponents. Power to a power means multiply the exponents. Distributing in the numerator is going to give us 2x plus 4. And power to a power in the denominator, distributing is going to give us 3x minus 3. Right-hand side, still the same. Okay, we need a single power over here. We have another exponent law called the product law that says if I have some power x to the power of a and I divide it by another power with the same base, we can simplify by keeping that base and subtracting the exponents. We go from having 2 terms to having a single term. Again, this only works when the bases are the same. So that's why we couldn't do this right off the bat. The bases weren't the same. But now that we have adjusted our bases, we do have the same base. So using this quotient law, we can go ahead and simplify that right-hand side to a single power. Keep your base of 5, subtract your exponents. 2x minus 3x is negative x. 4 minus a negative 3 is 4 plus 3, which is 7. So just watch your signs when we subtract there. 3x minus 7 on the other side. Now we have a single power, same base, simplified exponents. We can go ahead and equate those exponents. I'm going to go ahead and solve this. I'm going to, in this case, add x to both sides. So that's gone. We're just left with 7 on the left-hand side, 4x minus 7 on the right-hand side. We're going to add 7 to both sides. So 14 equals 4x. divide both sides by 4, and simplifying, we get x equals 7 over 2, or 3.5. So similar, we recognize we cannot do any simplification off the bat. We're going to write everything into a base of 5. We use our power to a power to simplify the numerator, power to a power to simplify the denominator, use the quotient law to get a single term on that side, equate the exponents, and solve. And one more time, let's go ahead and graph this to check. So we go to y equals, clear everything out of there. Okay. On that left-hand side, 25 to the power of x plus 2. Let me make sure I close this bracket here. Divided by 125 to the power of x minus 1. And then on the other side, just a 5 to the power of 3x minus 7. Oops, that's not what I wanted. Let's try that again. 3x, there we go, minus 7. Okay, let's graph this. We probably won't be able to see it. There's our exponential on one side. Here's our exponential on the other. I can't see it, but I think the calculator can still find it since the x value is small enough. y1, y2, and guess. We're looking for that x value of positive 3.5, and there it is. All right, so we have solved 6 different equations algebraically and checked them all graphically. So our next step is going to be to use these skills in solving application problems.